In this video, we will investigate one more example of how the derivative affects the shape of a graph. So for the given function, we are going to determine the intervals of increase, decrease, intervals of concavity, and then put it all together to provide a rough but hopefully pretty accurate sketch of the graph of f. So let's begin with increasing, decreasing. That requires us to find the first derivative and determine where it's positive or negative. So to differentiate this function, we are going to use the quotient rule. The quotient rule tells us that we take low d high minus high d low all over the bottom squared. So in the top you have x squared plus 1 minus 2x squared. That gives us 1 minus x squared all divided by x squared plus 1 quantity squared. To find those intervals of increase and decrease, we need to think about where this derivative is equal to 0. And where it is equal to 0 would occur when the top is 0. And notice where the bottom is 0, technically you can also change sign, but x squared plus 1 is always a positive quantity, so here we really only need to worry about where the top is 0. So the critical point would be x equals plus or minus 1. So we think about making our sign chart for f prime, and we want to know in between and outside of these zeros, or critical points, what will the sign of f prime be? So note f prime in the denominator is always positive. So really we just need to think about what's happening in the numerator. So if I plug in a number, say minus 2, you would have 1 minus 4, which is negative. In the middle interval, if I was to pick 0, when I plug 0 into the top, 1 minus 0 is positive. Remember, the bottom's always positive. So f prime is positive. For the rightmost interval, if I pick a nice number like 2, 1 minus 2 squared, 1 minus 4, that is, makes the top negative. So in terms of intervals of increase and decrease, our function f is increasing from minus 1 to 1 and decreasing outside of that interval. So that would be minus infinity to minus 1 along with 1 to infinity. Now we can do the same thing for the second derivative to determine those intervals of concavity. So for the second derivative, we need to differentiate the first. So once again, that's going to be something involving the quotient rule. So the quotient rule tells us low d high, so that would be x squared plus 1 squared times the derivative in the top, minus high d low. And when we differentiate that function in the bottom, we are going to have to use the chain rule. So we get the derivative of the outside evaluated at the inside multiplied by the derivative of the inside, and this is all divided by the bottom squared. And when you square a square, it becomes the fourth power. Now this is a very typical scenario, and at first it looks like there's an awful lot going on. But the simplest observation we can make is that x squared plus 1, x squared plus 1, x squared plus 1. So what we can do is cancel a single x squared plus 1 from each term. So the first term will have a power 1. The second term, the x squared plus 1 goes away. And in the bottom, the new power is going to be 3. And I'm going to rewrite that because I don't want it to look too messy here. So in the top, we have x squared plus 1 times minus 2x minus, we have 1 minus x squared times 4x, all divided by x squared plus 1 cubed. Then in the top, we just need to do some simplification. So that minus 2x has to distribute through and hit everything, and the 4x has to distribute through and hit everything. So when you do that, just kind of talking our way through the top, you're going to have minus 2x cubed minus 2x. Then you're going to have minus 4x, then minus a minus, so plus 4x cubed. So that gives us a total of 2x cubed minus 2 plus 4 of them. And then minus 2x minus 4x is minus 6x all over x squared plus 1 quantity cubed. And to determine those intervals of concavity, we need to know where is this derivative, second derivative, equal to 0. And that second derivative is going to be equal to 0 when the numerator is 0. Because remember, the denominator, just like in the first derivative case, is always positive. So 2x cubed minus 6x equals 0. So x multiplied by, so let's say 2x multiplied by x squared minus 3. So x equals 0, or x equals plus or minus the square root of 3. So when we make our number line for f double prime, we have to label 3 spots: minus root 3, 0, positive root 3. And just as a reminder, square root 3 is roughly 1.73-ish something. So we have 4 intervals to worry about for concavity, kind of to the left of minus root 3, then to 0, then to positive root 3, and then to infinity. And in terms of f double prime, remember, if we look at the denominator, it's always positive. So all we need to worry about is the numerator, which we've simplified here. Where is this quantity positive? Where is it negative? So if I was to plug in a number like, say, minus 4, you would end up with minus 8, a negative, times a positive. So f double prime will be negative to the left of minus 3. In between minus root 3 and 0, if I plug in a number like, say, 1, you would have 2 times 1, which is a positive, multiplied by minus 1 times minus 3. So you would have negative 2 multiplied by a negative, which would make it positive. Similarly, between 0 and root 3, pick the number positive 1. You'd have 2 multiplied by minus 2, which is negative. And then for outside of there, it becomes positive. So in terms of our intervals of concavity, we would be concave up from minus root 3 to 0, along with root 3 to infinity. And we would be concave down from minus infinity to minus root 3, along with 0 to root 3. So let's now put this all together just to give a sketch of what this graph will look like. Now below the xy coordinate system, I've indicated where our function is decreasing, increasing, concave up, concave down. But in order to make the sketch a bit more accurate, let me just note kind of 2 things. The first, just by inspection, this function equals 0 only when x is 0. So we know that we cross through the x-axis at 0. A similar observation that we can make is that if we take the limit as x goes to plus or minus infinity, doesn't matter which one, the degree in the bottom is bigger than the top. So that limit is going to be 0. So our horizontal asymptote is just the x-axis. So putting this kind of together, and to help sketch, I'm going to draw kind of a dashed line here where I change concavity just to help myself. So we know that we're approaching 0 as we go to minus infinity. And as we come away from there and we move to the right, we're going to be decreasing and concave down. So decreasing, concave down. But right when we hit this dashed line, we continue to decrease, but now we're concave up. When we hit minus 1, we're concave up and increasing. When we hit 0, we are increasing and concave down. When we hit 1, we switch to decreasing, but we remain concave down, and then concave up afterwards. And note that the function we're dealing with is odd, so it should be symmetric about the origin, and we do see that symmetry. If you take what's to the right, reflected about the y-axis and the x-axis, you get the origin symmetry.